In this little lecture, you're going to learn about the addition reactions of alkenes. There are many reactions, as you will see, but in this one, we will cover a small section of it. There are a few things to remember when we talk about the reactions of alkenes. The first is that almost all the reactions of alkenes are going to be addition reactions because alkenes are what we call unsaturated hydrocarbons. Unsaturated meaning that they can actually take in more molecules or atoms, and once they do, then they become saturated. So the alkenes are considered unsaturated, so addition reactions are common for alkenes. The other kind of reactions we will encounter are oxidations. These are slightly different than the addition reactions. So when we get there, we'll talk about that. And the third thing to keep in mind is that alkenes themselves are nucleophiles and they will react with electrophiles, okay? Because alkenes have the double bond, and so they will react as nucleophiles with electrophiles to give the addition products or the oxidation products. The reactions I'm planning to cover in this portion are the addition reactions, which are going to be the hydrohalogenation of alkenes, which is addition of HX. Now remember, X is halogen in organic chemistry. Then we'll talk about halogenation, where you add any of the halogens, which is group number 7. Hydration of alkenes, addition of water. Then there's a halohydrin formation where you add a halogen as well as water. Then we will also synthesize diols. Now this is kind of similar to hydration, where in hydration you're adding only one alcohol, but in diols you're adding 2 alcohol groups. Then we'll talk about carbene addition. Now carbene's a little bit different than any of the intermediates that we've learned about carbon. So again, when we get there, I will explain this a little bit more. Then we will talk about epoxides and then hydrogenation. Hydrogenation is addition of hydrogen, which is also considered a reduction on alkenes. It's still an addition reaction though. And then lastly, we will talk about oxidative cleavage. Okay, so these are the reactions we plan to talk about. Here are the reactions in terms of their structures. So here's your alkene. I've taken a very simple alkene, 2-butene, very symmetrical, nothing to talk about over here, but I just want to show you a little bit about all the reactions that we'll be covering. So the first one here, hydrohalogenation. So you add a hydrogen as well as a halogen. Halogenation, adding one molecule of a halogen, which means 2 atoms of a halogen. Hydration, adding water, HOH, so H2O. Halohydrin, so you're now adding a halogen as well as an alcohol group. Then here is the diol formation, and here are 2 alcohol groups. I want you to note that in all of these cases, whatever is being added to the double bond, which means that it's a 1,2 addition, or as we say, it's adjacent carbons, okay, alpha, beta, 1,2, but these are all getting added to the double bond, okay? So, and the final product, there is no double bond there, addition reactions, right? And then here's the carbene addition. The purpose of carbene additions is really to synthesize cyclopropane rings. Okay, and you can see it's a very small ring over here. We've talked about the fact that cyclopropane rings are highly unstable and very high in energy, okay, because of the angle strain, but you can still make them. Okay, so this is how we make them using carbenes. And then here is epoxide. Epoxide is also a 3-membered ring, but now you actually have a cyclic ether, carbon, oxygen, carbon. So this is a cyclic ether, and we've synthesized ethers before in SN1, SN2 reactions. In fact, most of the compounds we synthesized were ethers, but now we'll be talking about a cyclic ether. And epoxides are very specific in their nomenclature, meaning it's a 3-membered cyclic ether. So that's epoxide, so we'll make these. The last addition reaction that we have is that of reduction. So we're adding hydrogen, and that's why you don't really see any other heteroatom over here. And then finally, the oxidative cleavage. And you can see, looking at this reaction itself, that there is something different going on here. First of all, you started with 1 molecule and you end up with 2 molecules, okay, over here. And that's the part of the cleavage, which means that something is getting broken. And the oxidative part tells you that there is oxygen being added here. So these are all the reactions that we will cover. A little bit about the general mechanism. We will cover the mechanism individually also as we go on for all the reactions, but just to get you started, okay, for some of the mechanisms, because there is a general trend for all the addition reactions. So first of all, again, alkene is the nucleophile here. Whatever reagent you're going to be adding is the electrophile. Okay, and the alkene is the nucleophile because alkene has the double bond, which is electron rich. Okay, and so here is a reaction. And here is the alkene, which is the nucleophile, and here is the electrophile. This is HX, and if you can think about HX as being HCl, hydrochloric acid, then it'll be a little bit easier for you. So if this is HCl, then this is the base, okay? Because this is the acid, this is the base. So which means that your electrons will transfer from the base to the acid. Now, because we're talking about a traditional acid over here, HCl, which means they are proton donors, the double bond here will go for the proton. Okay, now remember it's a double bond that's going. There are no extra electrons on carbon, either one of those. The electrons reside in the double bond. So you have to start the arrow from the double bond, pick up the proton, and then the proton leaves with its electrons on the halogen. And then this is what you get as an intermediate, which is a carbocation. So now you have these two carbons. Now remember the bond that we used to pick up the hydrogen, those extra electrons, those are right over here with the new bond with hydrogen. You have to place the hydrogen either on this carbon or this one. Okay, because that's where the bond is breaking. So hydrogen can go on either side of the carbon. Right now we're going to go ahead with the left over here, but later on you will see that things can be a little bit different. So one of the carbons will get the hydrogen, the other one will get the carbocation because it has fewer electrons now or less electrons, and then here is the conjugate base. So which means now we've reversed everything. Now the carbocation becomes the electrophile, okay, because that is electron poor. The conjugate base now is your nucleophile that will go ahead and attack the carbocation, and here's your addition reaction, HX, HCl added. Okay, so it's really all about acid-base reactions, electrophile, nucleophile, and if you want to think about it from Lewis acid-base perspective, any one of those will work. The other thing I want to mention over here, okay, is the fact that there are two kinds of alkenes. We've talked about this before also, but just a little review, is that there are two kinds of alkenes, symmetric alkenes and asymmetric alkenes. In symmetric alkenes, the double bond is symmetric, okay, which means that it has equal number of hydrogens and carbons, okay, and so this is what a symmetric alkene would look like. It would be fine if it was cis also, okay, it doesn't really matter because even then you will have one carbon, one hydrogen on one double bond and one carbon and one hydrogen on the other double bond, on the other carbon. So it will still be symmetric, whether it's cis or trans, it doesn't matter. Here, however, this is asymmetric double bond because now on the double bond on one carbon, you have carbon and hydrogen, whereas on the other carbon, you have two carbons, okay? And so this is an asymmetric alkene. Both of these represent the same structures. Over here, I just removed the hydrogens, okay? Because you have to be able to see structures without the hydrogen. So the right side is kind of what it looks without the hydrogen. Anyway, this is not new to you. In any case, so remember that there are two kinds of alkenes, symmetric and asymmetric. So let's talk about the first addition then, hydrohalogenation. Okay, and hydrohalogenation, we will cover this both for the symmetric alkene as well as the unsymmetric alkene. Okay, as we say, because the addition is different for both of them. So here is 2-pentene, which is a symmetric alkene because both of them have a hydrogen and a carbon, a hydrogen and a carbon attached to it. So when you add HBr to it, then you end up getting two products because at one time the H can go to the left carbon, okay, or at one point the H can go on the right carbon, all right, and so the bromine then is left to go on the other carbon. So you end up getting two products, which is 2-bromopentane and 3-bromopentane. And sadly, you can't do anything about it. So which means that if you take 2-pentene and you do the addition reaction with HBr, hydrobromic acid, you are going to get these two products in equal quantities. If this was symmetrical, for example, if this was 2-pentene, 2-butene, then it wouldn't really matter because if you look at the nomenclature of them, they would be both same. However, when we go towards the unsymmetric alkene, now things are going to be slightly different, okay, and in case of asymmetric alkenes, we follow what is called Markovnikov's rule, And obviously Markovnikov was the one who came up with this. And what he found is that if you take an asymmetric alkene, so for example 2-methylpropene, where one carbon has 2 hydrogen and the other carbon has 2 carbons in it, then if you add HCl, then invariably the carbon with the more hydrogen is going to get the hydrogen, all right, and the carbon with the less hydrogen will get the chlorine, all right. So carbon with the more hydrogen gets hydrogen, and that is called Markovnikov's product, all right. And the other one, in which the chlorine is going to go to the carbon with more hydrogen, is called the anti-Markovnikov's product, which in this case does not even form, okay, which means that the only product that will form is going to be the Markovnikov product. And again, Markovnikov addition is where hydrogen goes to the carbon with more hydrogen. That's Markovnikov's rule, and we follow it, okay, follow it in the sense that it is true, okay, and we'll talk about why it's true. So initially when Markovnikov came up with this rule, the mechanisms were not quite understood, okay, at that point. But once the mechanisms had been established, it is easy to figure out why we would get Markovnikov's product, okay. So here, let's go ahead and write the mechanism now. So when HCl adds on to 2-methylpropene, you can get two kinds of carbocations, because the hydrogen can go to the left carbon, or the hydrogen can go to the last carbon over here, okay, the carbon with more hydrogen, because remember, this is the double bond that's attacking the hydrogen. So hydrogen can go on either one. So here is the top one, okay, where hydrogen goes to the carbon with more hydrogen, forming this wonderful carbocation. And then here is the other attachment where hydrogen goes to the carbon with more carbon instead of hydrogen. And then this is the carbocation you get. And so looking at these two intermediates, we know from SN1, SN2 reactions, especially SN1 reactions, that tertiary carbocations are way more stable than primary carbocations, and of course tertiary are the most stable from secondary and primary also. So this carbocation will be formed a lot more, and therefore this will be the predominant product, which means that now when the chloride adds, it will add to the tertiary carbocation. However, the primary carbocation never forms because it's not stable, okay, and hence you get the Markovnikov product, okay, when you have an asymmetric alkene, purely because of the stability of carbocation. One of the things that we've encountered before also in SN1 reaction is rearrangement of the carbocation. And since we've seen the mechanism now for the addition on alkenes, it is primarily through carbocation formation. So which means that we have to look out for the possibility of rearrangements. So let's take this example where we have 3-methyl-1-butene, 1, 2, 3, 4, okay, 4 carbon. And then here is the alkene, and you add hydrochloric acid to it. And what you would expect is that the hydrogen will add on to the carbon with the more hydrogen, and the chlorine will add on to the second carbon over here, which is this product, okay? So 2-chloro-3-methyl-butane. This is the one that you're expecting. However, you do the reaction and you end up getting one more product, which is 2-chloro-2-methylbutane, which means that we got the addition on this carbon of the hydrogen, which you expected, but the chlorine did not add over here. The chlorine actually added on the next carbon over. So then you have to start thinking about, how did I get this product? And it is approximately 50-50 mixture. So which means that there is something serious going on over here. It's not just a minor product, it's quite the major product too. So we have to look at the mechanism again, okay, for this one, and see what is possible. And so let's start with the mechanism here, with the double bond attacking the hydrogen, picking up the hydrogen here and forming the carbocation. But then what happens here is, because this is a secondary carbocation, you can get a hydride shift, okay, from the next carbon over to this carbocation, and so then you will end up getting a tertiary carbocation. And as we know from before, is that tertiary carbocations are more stable than secondary carbocations. And so this kind of a hydride shift leads to more stability of the carbocation. Once this happens, then you end up getting the second product, which you were not really expecting because we did not think about rearrangement before. And then here with the secondary carbocation, you can also get addition. Now secondary carbocations are fairly stable, so you will still get some product. If it was primary, you may not have gotten a lot of product. It would be probably a minor product. But because it's a secondary carbocation, both of these products are almost equal in quantity. And this happened only because of the rearrangement, that you ended up getting two products. If there was no rearrangement, obviously you'll have only one. So, and remember again, the rearrangement happens only to give the more stable carbocation. Otherwise, rearrangement is not going to happen. The other thing you need to remember is that the rearrangements that you do are for small things like hydrogen, methyl, and phenyl. Phenyl is a little bit of a big group, but you can have a hydride shift, a methyl shift, and a phenyl shift. You can't shift ethyl groups or big groups like that, okay, or any other thing. So those are the shifts that you will get, all right? And again, the rearrangement is primarily to give more stability. The next addition reaction is halogenation. Halogenation is, of course, addition of a halogen. Bromination and chlorination are usually the two most common molecules that are added to give the dihalides. Fluorine is very reactive, and I2 or iodine does not really add very well. Okay, and remember, iodine is a huge molecule, and so it's quite stable on its own. And then fluorine is too small and it's very reactive. So it's preferable to do bromine and chlorine additions only. Also, from our previous understanding of SN1, SN2 reactions and substitution reactions, you know that bromine and chlorine are more versatile in reactions than fluorine and iodine can be. You can use them as leaving groups, and so they make for really good starting materials. So this is a very good way of making a starting material for SN1, SN2 reactions. So in any case, so bromine and chlorine are the ones that we will work with. Note over here with the qualitative test, I will talk about that in a minute, okay, with bromine. So anyhow, here's the addition reaction where you have an alkene. You add chlorine to it, and chlorine adds 1 and 1 or a 1,2 addition of chlorine happens. Now, there are a few things that are important. For example, when we talked about the addition of HCl or hydrohalogenation, the addition was Markovnikov addition. Now, in this case, the important thing to remember is that the addition is a trans addition. So what does a trans addition mean? This has to do with the mechanism of the reaction. So here, let's see this. If you have, say, cyclopentene that you're working with and you add bromine to it, this is a very strange thing because the double bond will attack the bromine, and the bromine in turn will attack the carbon, and the other bromine is going to leave. This is a little bit weird reaction because bromine itself is not polarized at all. The only way that a double bond will pick up a bromine is only if it was an electrophile, because remember, the double bonds are nucleophiles. So this is a little bit of a different reaction, and this is the best mechanism that is possible, okay, to give the kind of products that we are expecting. So the double bond attacks the bromine, bromine attacks the carbon right back, and then here the bromine is leaving, okay, so which means we have a bromide ion in solution. So once this bromine is attacked by the double bond, it ends up forming this kind of a ring, which is a three-membered ring, and this is called a bromonium ion. If it was chlorine reacting, it would be called the chloronium ion, and you end up getting this kind of a cyclopropane or a three-membered ring. And what happens is, because this is a three-membered ring, the other bromide that has to come, it will come from the other side of the ring. And when it comes from the other side of the ring will open from the other side, which means from the opposite side. So which means that the two bromines that are added on, they will actually be added on onto the opposite sides. Okay, so when the bromide attacks over here, the bromonium ion is relieved and it gets its electrons, okay, and so you end up getting this bromine here, and then the bromide ion, which came from behind over here, is on the other carbon. So which means that the bromines are actually adding on opposite sides, and this is called a trans addition. This will happen whether you have straight chain or cyclic. It's a little bit easier to see on cyclic, that's why the mechanism is given here, but otherwise, even for straight chain alkenes, that's the addition you will get. Now remember, the cis and trans, or this kind of an addition, the trans, can give you stereochemical products. In some cases you don't see that stereochemistry. So for example, here these carbons are not stereoactive, and so you will not see the trans addition in small molecules like this. But in some cases like cyclopentene, you will see the trans addition quite evidently. Now for the hydrogenation of alkenes, which is the addition of hydrogen. And this is classified as both as an addition reaction as well as a reduction reaction. And so hydrogenation of an alkene will give us alkane. This reaction is quite common, but it's also very hard to do because it's very hard to get the alkene and the hydrogen to come in the correct orientation so that they can react with each other. So in order to help with that kind of a reaction, you need a catalyst. Okay, and so you use platinum, palladium, nickel. These are all heavy metals in transition series, if you see, and they're used in order to catalyze this reaction. Okay, if they're not used, then this reaction is very hard to do because hydrogen is a very small diatomic molecule, and because it's very small and light, it's always moving around, and it's very hard for it to be in the correct orientation, okay, with alkene in order for it to react. So the platinum, palladium, or nickel provides the little background or the little surface, okay, that it needs to hold on to, and then it can do the reaction. Okay, so when you look at the reaction for any kind of hydrogen, okay, or any hydrogenation or reduction, you will see that you have the hydrogen there, but you also have a heavy metal there. The heavy metal may be as platinum oxide or palladium carbonate or something of that sort, but you will see a heavy metal in there, okay, and that means there is hydrogenation going on. The addition that we have for hydrogenation is also a syn addition, which means it's happening on the same side. And the mechanism can be explained like this in the diagram shown below, where you have the metal surface. The hydrogen actually bonds to the metal surface. It has specific affinity to these metals. That's why we don't use copper or cobalt or silicon or something like that, because these metals, platinum, palladium, nickel, these are the ones that bind very nicely with hydrogen. This process is actually called adsorption, which is AD, not AB, absorption, okay, adsorption. And in case of adsorption, the hydrogen is just on the surface of the metal. And so what happens then is the alkene will come around, and then it will also be on the surface of the metal. And once it's on the surface of the metal, it will just pick up the hydrogen and then move on. Okay, so which means that the hydrogens are being added from the same side. Okay, and so that's the role of the platinum palladium, okay, which is the role of the catalyst, is to give a linkage, okay, to the hydrogen, okay, which otherwise will move around. And that is also a reason why this addition is always going to be a syn addition or a cis addition. Now we go on to something which is slightly different than what we've been doing before, and this is the reaction of alkene with carbenes. So first of all, what is a carbene? If you take an alkene and you slice it into half, okay, which means that each of the carbon gets the pair of electrons that it has, because remember there are 4 electrons here, 2 pairs of electrons. So if one pair goes to carbon and the other pair goes to the other carbon, you end up getting something like this, okay, which means a carbon with a pair of electron. And that is what is called carbene. So which means that it is neither positive nor negative, but it has a pair of electron. It is considered to be electrically neutral. Okay, so which means again, no positive, no negative, it is just neutral, and it has a pair of electrons. That's how you identify a carbene. Anyway, so an alkene can react with a carbene to give a cyclopropane ring. Depending on what is attached on that carbene, RR, those RR can be hydrogens or it could be other groups. Okay, and so this is what you end up getting. And again, this reaction is specifically to make a cyclopropane ring. If you did not want a cyclopropane ring, you would not use a carbene, because then this is the only reaction that is possible, okay, with the carbene and an alkene. So this is how you would generate a carbene, all right, which means that you take diiodomethane. Now remember, we haven't really used iodine before, but it's a very specific reaction. This is called the Simmons-Smith reaction, and in this case you will take the diiodomethane and you treat it with zinc and copper alloy, and once you do that, the zinc and copper will react with the diatomethane to give you the carbene, okay, over here. And this carbene is right here actually, but it's bonded with the zinc also, all right, and that's why you can't really see it very clearly. So this is isolated for you over here. So once that carbene is generated, then it will go ahead and react with the alkene. Okay, so this is how you would actually write the reaction out, where you have the CH2I2 and then the zinc and the copper, and ether is the solvent over here. So the carbene that is generated as a result of these reagents will then just add on to the alkene. Addition is syn. Okay, as you can see from here, that we have the bonds going on the same side. They cannot be anti, okay, because it's such a small ring, you can't have the addition going on opposite sides, okay, and so this is a syn addition giving you a CH2. And this is another example of the addition of carbene, and this is dichlorocarbene. Okay, this is coming from chloroform, which is CHCl3, with in presence of a very strong base like potassium hydroxide. The potassium hydroxide will abstract HCl, okay, from here. Once it abstracts HCl from chloroform, all that is left is CCl2 with the electron pair. The CCl2 that is left over is what is actually adding over here. This is one of the reactions that you will be doing in your labs. I think it's an organic too, most likely. But in any case, this is what you end up getting. Now here, instead of hydrogens, you actually have chlorine. Which one you want to make is, of course, depends on what you need. Okay, so again, the addition is syn, and this is carbene chemistry. The takeaway from this lecture and this addition reactions is that you should understand the electrophilic addition, where the alkene is the nucleophile or the Lewis base. You should know the Markovnikov's additions, syn addition, anti-additions, hydrohalogenation, halogenation, of course, carbene, and then hydrogenation, and the characteristics of all of these, okay, whether it's Markovnikov addition or syn addition and things like that.